Hi ladies and gentlemen, welcome back to my channel. Today we're going to look at FM transmitter. Right here on the screen you can see a circuit diagram of an FM transmitter. A little while ago when we started using FM transmitters, we wanted to build something that is unique and very simplified. And what we did was took a transistor, an NPN transistor, configured it as a simple amplifier. So you can see a biasing resistor right here from the positive rails to the base of the transistor. If you remember, we talked about transistors. So NPN transistors, why don't I just show you right now one of the things that I need you to know about transistors. Okay, to bias a transistor you need to know these principles. So I'm gonna hide the screen and this screen and just go straight to this window. Right, and to get my pen. Right, so if you have a transistor, just draw a block like this, or two blocks. Okay, actually draw two blocks this way, and then divide it up into three, each of the blocks. This is a very simple trick. If this is an NPN transistor and this is emitter, base, collector. Now the base is the one that is odd. So because you also have PNP transistor, right? So if I draw another block for the PNP transistor, it will be P and P. The one that is odd is always the base. Now let's look at the NPN transistor, right? Let's use green marker for the NPN transistor. So for the NPN, just draw something around this block this way. And for the PNP, let's use a different color. Let's use red for the PNP. So draw, okay, no, we already used red. So let's use a different color. Let's use this color, or blue. Let's use blue color for the PNP. Now, one thing you have to notice is for the NPN, the base, the emitter, sorry, is always the most negative. Always the most negative. Again, I'm using the wrong pen, so let's change the pen and let's use green again. The emitter is always the most negative. And for the PNP, we're going to go back to blue. For the PNP, the emitter is always the most positive. Always. So when you have this in mind, it becomes a little bit easier. The rest, we go less that way, less that way. So it will be less positive, less, let's say, less positive. This should be less negative. Always the case. Less negative, less positive. So this is more negative. This will be negative compared to this. So let's put a value. Okay, let's put a value. Let's say this is 3, right? If in terms of being negative, the emitter is 3, the base is 2, and the collector is 1. So also here, if 3 is more positive, then here will be 2 and here will be 1. So I'm using the wrong pen again. So let's change the pen to red. Blue, sorry, we need blue for the NPN. So if this is for the PNP, if this is 3, this will be 2, this will be 1. In terms of negative. In terms of positive, sorry. For the NPN, it's the other way around. The emitter is the most negative, followed by the base, and then the collector. Okay. So let's go back to the circuit. This is what I just wanted to show you right now. So we're gonna go back to our circuit. So the circuit we have here, we want to pull the base to positive with respect to the emitter, because the emitter is the most negative. Let's go back again and look at that again. The emitter, remember, the emitter is the most negative, right? So for the NPN transistor, um, let's hide this other displays, and we're going to show the one note one more time. So here, for the NPN transistor, the emitter is the most negative. The base is positive with respect to the emitter, right? So this is less negative. In other words, it's increasing in positivity. So less negative, or we can just use the word more positive, right? So let's use a neutral marker here so we don't have to change it all the time. So this is increasing positivity, more positive. Um, this looks like a greater or equal sign, but that's not what we meant. So it's increasing positivity, increasing positivity, more positive, more plus, or less negative. This is, in this way, it's less positive or more negative, right? So for the PNP, the emitter is the most positive, and then the collector is the most negative for the PNP. For the NPN is the other way around. All right, so let's go back to this window here. Right, so we put up the base to bias this transistor, and then we played around with other components, and we got it to oscillate. Now the key that I want to discuss today, why I want to make this video, is this tank circuit. One of the circuits we made, people were asking us to give them the value of the inductors or the value of the capacitors, and there's a lot of questions that we received on that. And we thought it's good to make a video that explains this theory, and that's why we're doing this today. We're going to demonstrate it with a circuit that we've already built. We're going to show the circuit today. We're going to demonstrate the circuit today, and you can see the function, the role of this tank circuit. So let's go back to the window that we were looking at earlier on. So here I'm going to redraw the tank circuit. Tank circuit is made up of an inductor, so, and the capacitor connected in parallel. In this case, we're using a trimmer capacitor. So this is my inductor, and this is a variable capacitor. These two components are your tank circuit that determine the frequency of an oscillator. Okay, so I'm going to leave this and come back to it later. When I was a young boy and I was trying to learn how to build transmitters, there's one thing I read in one of the books at the library. That was in my secondary school, secondary school, Akanano, Enugu, in Nigeria. One of the things I read in the book that helped me a lot to understand the functions of an oscillator has stayed with me till now. And this was a book written for younger people already when I was in JS2. There's a grade, what grade is that? Grade 8. So they said you build an amplifier. So the first block is an amplifier. The next block is your frequency determining network. The next block is your feedback network. So to build an amplifier, to build an oscillator, so this block gives you an oscillator. So basically, you build an amplifier, you send it to another block that is the frequency determining network. Let's change this ink to different color so that we can, when we overwrite something, we can still see the new addition. This is a frequency determining network. Once this is done, you need to take a portion of that output and feed it back into the input of your amplifier. When you do this successfully, you have created an oscillator. And this is the building block of every transmitter. You need an oscillator. At the core of every transmitter is an oscillator. So you have an amplifier, you have a frequency determining network, feed that back to the input, and that loop continues, and you have an oscillator. A transmitter, whether it's an FM transmitter or an AM transmitter, requires a carrier frequency. Alright. So the carrier frequency here is determined by the tank circuit. So let's go back to that. Alright. The carrier frequency, or our frequency determining network, is this block here. And the frequency is 1 over 2 pi square root of LC. The L and the C are these components here. So when you ask me a question of what's the value of my C or the value of my L, it is more of what is the value of the combined components. It's not about the L or the C. You can make a different L and make an equivalent C such that the circuit will respond to this formula. As long as this formula is observed, you are okay. Your frequency, I call it FO, the fundamental frequency here, is a function of the L and the C. 2 pi are constants. 1 over 2 pi is a constant. So you're only concentrating on the L and the C. Right? Give me a value of L, I will find the value of C. Give me a value of C and I'll find the value of L for any given frequency. So let's go back to that circuit, right? Right, the circuit that we're talking about here is right here. My L and my C, the value of the L and the C will determine the frequency of this circuit, and that's basically it. The rest of the component you see is we trying to figure out which is the best place to put your antenna. We've seen some people put the antenna at the emitter circuit, others at the collector circuit. Play around with both and see what works best for your configuration, your particular configuration, right? So in our case, we've tried it in both and they both worked. But you can try it and see which one works best for you. The rest of the components are the RF amplifiers to boost the RF signal coming from this circuit. So in this case, we're taking the input of the RF amplifier from the collector circuit, and I think that's where our antenna comes from. That's it basically. Bias your transistor as an amplifier, have a frequency determining network connected to that amplifier, take a portion of it and feed it back into the input circuit. In this case, this is a common emitter circuit, so anything you feed to the emitter is also going to be part of the input circuit. So take a portion of that, feed it back into the input circuit, and then the loop continues, right? So remember I said you need a carrier frequency, and then you need the modulating frequency, or the signal you want to transmit has to be modulated over the carrier frequency. So for amplitude modulation, you're going to modulate the frequency of the amplitude, the amplitude of the carrier signal. For frequency modulation, you're going to modulate the frequency of the carrier signal. So in this case, we're modulating the frequency of the carrier signal. One more thing here to note is that this oscillator is a voltage controlled oscillator. In other words, as the voltage change, the value of the voltage changes, so also the frequency. So this is not a very stable system. This wireless microphone is not stable, right? Unless you can, one way to make it stable is to include a voltage regulator somewhere in the power circuit. Include a voltage regulator and then increase your voltage source. Let's say you have 4.5 volts here and you have a 1.5 volt voltage regulator. You can build this using a Zener diode, right? So if you have a 1.5 volts regulator connected to this circuit, then you are sure that as long as the input voltage is greater than or equal to the regulator voltage, then this circuit will function stable. And also it's sensitive to touch and other, because of capacitance, right? The capacitance is affected by the presence of, not the capacitance, sorry, the inductance is impacted by the medium, by the epsilon of the medium. So when you come closer, you're changing the the epsilon of the medium, and you're changing the value of the capacitor, the inductance. Sorry, not capacitors, inductance. So you're changing the value by being closer to it. And if you have long leads connecting this, you're also changing the capacitance, because the capacitor is just parallel conductors. As you increase the length of the conductors, you're increasing the value of the capacitance, or affecting, let me say, affecting the value of the capacitance. And also, if you have long leads on the inductor, you're also affecting the value of the inductors. Now, so this is the circuit. We've already built it. We're going to experiment on this. We're going to turn it on and see how it functions. And I will show you that the value of the capacitor alone does not determine the frequency. The value of the inductor also plays a role. You're going to see this very clearly. So let's turn on the circuit and let's make it work. All right. So right here, so the circuit is on right now. We're just going to turn on the receiver, and let's get the receiver to function. All right. All right, this is the receiver, right? So we turn it, we put the receiver on, and there's right there you see um, the SDR. Remember last time we demonstrated this SDR receiver? So let me pull it up. You can go and watch the other video where we talked about the SDR receiver. So let's see. All right, right here is the sound. Let's increase the volume. Hello. All right, thank you. So it works. This transmitter is functioning right now. Turn it. Make sure I'm at the right place. Can you hear me? All right. I think you can hear me. Hello. Hello. Now, all right. So as I come close, I'm affecting the value of the voltage. But anyways, you can see it's transmitting around 87.4 megahertz. Now I can change the value by just adjusting the voltage. So hello, yeah. As I change it, you can see practically running. You can scan through the circuit by changing the value of the inductor. Just change the length of the inductor. Now I've made it very properly. Then let me turn it back. So the inductor alone can be used as a tuner. Right. So the inductor can be used as a tuner. So I can also tune the capacitor to tune the frequency. So just give me a second. And we are back. Alright, so I'm going to take a tuner. Let's get the right size. Just begin it tuning. Alright, so I'm going to change the value of the can you see that? We are expanding there. This time around I'm changing the value of the see it's going through. And right here, this is where I am right now. So I can tune it up. So then so now I can go there and keep pressing right there. So now I'm broadcasting on a different frequency. Now I don't want to be on the FM range, so I'm gonna go a little bit lower. So let's say let me go down to about 84. Let's get it to 84. So let's use the inductor this time. So pressing the button together. So let's go down here and see where we are. And with the combination of those, we are where we are. Yeah. So we're now around 84 megahertz. Alright, so we can let me just increase the volume a little bit. So we can go to another frequency if we will. Why not? Why not? So we can just use the trim again. So really the value is not that important. What is important is the combination of your tank circuit. Alright? So I can go lower. You can go to 27. The best thing is to go to the amateur frequency band. Or you can go to the band that is in the region if you want to build this. So let's try going down a little bit more. You have to adjust the vector and also alright, so the more I adjust the frequency, remember the presence of this actually also affects the vector. Just putting something into the vector would affect the vectors of the vector, right? Okay, I'm gonna use the trim of the small size. Is right now I have a broadcasting on the frequency. Alright, so this is a FM transmitter. Right now broadcasting at 82.6 megahertz. And if your antenna is not better than this is just the proof of concept. But you can make your signal. We haven't done any packaging here, just to demonstrate the function. Alright. And right now we're using 1.5 volts battery. Most of these companies are put on straps. So if you have some old electronic circuits, you can grab some of these. And once you can buy them, they're very cheap. Alright, so thanks for watching this one. And also, this is the basic building block of our FM receiver. Same principle. So you can actually use this to prove the inductance of your inductors. If you have a fixed value of capacitor, you can calculate using that formula I showed you, 2 pi, F equals to 1 over 2 pi square root of LC. If you know the value of your C, you can calculate your L. You can just do reverse engineering in that sense, right? And if you know the value of L, you can find the value of your C. But in most cases, you can find a fixed value capacitor and then just build an inductor. So this inductor is just a piece of wire. You round it, make it in a spiral or in a wound it on a cylindrical rod of about 5 centimeters diameter and get about 5 tons, and you should be fine. And even if it's less than that, you have seen that you can adjust the magnetic circuit itself, the inductance circuit, just the gap between each turn. When you make it wider or narrower, the value will change. The tighter it is, the lower the frequency. The wider it is, the higher the frequency. It just goes in that linear order. Tighter frequency, wider, higher frequency. Then when you have that combination using that tank circuit, L and C, using the formula F is equal to 1 over square root of 1 over 2 pi square root of LC. When you use that, you're going to build a circuit that will correspond to the frequency of choice once F and C match, right? So go ahead and do that and leave a comment and let us know. If you want to build a radio, just repeat the same circuit Let me just throw up the circuit again, let it freeze a little bit for a couple of minutes. You can also pause the video and get the circuit yourself. Um, but build a circuit, and you can use the same as a radio receiver. I'm going to show you back on the screen. So let's go back, and I'll show you again on the screen. So right here, um, let me pull it up on my screen. Right, as you can see, this portion where you have the second transistor, you can actually, let's zoom in a little bit, it's so tiny. Yeah, where you have the second transistor, you can use this as an audio amplifier, and then have this output here, you have your speaker, and this can function as a radio receiver. Many people have built this. We've done this already. So I'm going to put a link to our FM radio receiver to this video so you can watch that and build this circuit. So again, I said I'm going to freeze this. So let me make it a little bigger before I freeze it. So I'm going to freeze it here for a minute for you to copy the circuit. And you can also freeze it yourself and copy the circuit. Right. Alright, thanks for watching, and I'll see you in the next one. Alright, just stay creative, keep working through things, and you're gonna face some challenges. You're gonna have some questions initially. Ask, and we will help as much as we can. Alright. So I guess this clears the question, about what value we need for inductor, what value we need for capacitor, and so on and so forth. You don't really need that. Okay, this value doesn't belong here. It's 30. I think it's variable, right? 30 PF variable, but it can be any value. And the inductor is also variable, so I should have changed this value to variable. Anyways, these are virtual components. This just shows you the circuit layout. And what I have in my hand right now doesn't include this section. It only has from this portion to this wasn't included. So I'm gonna remove things that are not included so to avoid confusion. These are not included. You can use this as extra additions. So these are not included. Yeah, all these are not included. So you just have your antenna. So I'm gonna where is that? I think ground. Yeah. So you have your antenna. Go there. Where is the ground? Again, I need an antenna connection. So this is what you have in this circuit right here. Alright. This is just our meter when we're measuring the voltage. But something is missing here. Yeah. So this is the circuit. Very simplistic. You have about 8 or 9 components. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9 components. These are us measuring the voltages and trying to see what's going on at each point. When we bias the transistor, we wanted to see how much voltage we needed to bias the transistor. So these other components are not necessary. It's cleaner right now, so let me freeze it now for you. Yep. So this is the circuit you need. 1, 2, 3, 4, 5, 6, 7, 8 components, 9. This is us. Okay, make this. You can make this 1 microfarad. Doesn't matter. 1 microfarad. Yeah, and this here, you can make the value 2.2 kilohertz, 2.2 kilo ohms, 2.2 kilo ohms. Right. These are the realistic values we use in the circuit: 2.2 kilo ohms and 100 ohms. Right here, you can use 100 to 150. Doesn't matter. You can use 101, 103. The most important thing here is that you bias your transistor. So do this the way we did it. When we did it the first time, we didn't have this simulator, so we use a 10 kilo ohm resistor here, a trimmer resistor, and trimmed it until we get this to turn on. We get the value that turned this transistor on, and it was around 2.3 or 4 kilo ohms, and we found a practical value is 2.2 kilo ohms. We'll put it here, and then this, you play around with this component, these components, the inductor and the capacitor, using the formula we mentioned earlier on. Once you do that, I'm going to throw up the formula one more time. So let's go through this again. Build your amplifier. Okay, let's go through this. You're gonna go to the one note, right? It's gonna show other things on the screen, which is fine, but the one note is very important for us to understand what's going on. So let me turn off these and just go to the one note. Right. So you need, this is what you need. Build an amplifier, any amplifier of choice, preferably a one transistor amplifier. Have a frequency determining network, which is your LC tank circuit. Then have some form of feedback to the amplifier. You build an oscillator. Then just find a way to modulate it. You modulate the frequency, or you modulate the amplitude. If you modulate the frequency, it becomes frequency modulated. If you modulate the amplitude, it becomes amplitude modulated. Right? You can also modulate the phase, and you have phase modulation, and so on and so forth. But these are the most common ones for you to build. So amplitude modulation and frequency modulation. Some people also use crystal oscillator. Remember I told you this oscillator is a voltage controlled oscillator. So if you're trying to build a more stable transmitter, wireless microphone, I would recommend using a crystal oscillator. But this is what you need. And then once you get your tank circuit, and then the formula, observe this formula: F is equal to 1 over 2 pi. So this 2 is actually under, right? So 1 over 2 pi square root of LC. When you do this, you're gonna get a value of F, and you can use different values of C's and also corresponding value of L to get the same F. Let's say your L is 1 and your C is 2. You get a particular frequency. If you change your L to 2 and your C to 4, you get the same frequency, right? If you change your L to 2 and your C to 1, sorry, this will give you a different frequency. Let's keep it the same frequency. So if you change L to 2 and C to 1, you get the same frequency, right? As long as the unit, if this is microfarad, microhenry, and this is microfarad, microhenry, microfarad, you get the same frequency, because the product of those and the square root of the product. So the product will always be the same, and the square root will be the same, right? Here the product will be 1. Sorry, the product will be 2. 2 times 1 is 2. Product here is 2. So the product here will be 8. So the frequency will be different, right? So this will give you higher frequency. This will give you lower frequency, right? The higher the values here, the lower the frequency. Why? Because these are in the denominator, right? So the more they increase in value, the 1 over the value, the function will be less, right? So the more your inductance and capacitance, the less your frequency. So if you want to get a very, very high frequency circuit, this tells you have to go for very, very low inductor and capacitor, right? So another way to look at this, to make it just visible, is you ignore the constants and just say that f varies inversely as the square root of L and C. Just look at it that way, forget about the 2 pi's. So the more the values of these increase, this becomes lower. So just look at it that way. You can see the square root of L3, it varies also 1 over f. So look at it this way. When you increase value of this, this reduces. So they vary inversely. The more the LC, the less the F. The more the F, the less the LC, and so on. So how much value do you want for your F? If you want a very, very high frequency, you need a very, very... That's why in your phones you have very small inductors and capacitors, because they go for higher frequency, talking about 800 megahertz and above. And if you want to go to gigahertz, even sometimes you don't even have physical inductors, you just have small components, 0202, 0204, 0202, very small components functioning as capacitors and inductors. Sometimes a straight wire, depending on how high the frequency is. Just a very short wire, microstrip, is all you need to make an inductor, depending on how high the frequency you want to make, right? Alright, so I think that will be it. Remember again today, when we pressed the inductors tight, the frequencies were decreasing. So which means we're increasing actually the inductors as we pack them together. The frequencies were decreasing. As we spread them out, the frequencies were increasing. So when we're spreading it out, we're reducing the inductance, and the frequency were increasing, right? Alright. So this is what I want to show you today, and I think that will be it for today, and I will see you guys on the next one. So remember to subscribe to the channel. Alright, we can stop broadcasting right now. Before we stop broadcasting, why don't we just show the SDR one more time? Let's see SDR. So you can see we've been stable on that particular frequency for quite a while, so the battery is still good. As soon as the battery starts running low, the frequency will shift. Or if I put something close to it, let's try a magnet. Let's try a magnet around it and see what it does. Whoa. The magnets change the frequency. Okay. So I'm just gonna put it away because I have a computer here. I don't want a magnet by my computer. Anyways, so as we change the value of the inductance, if I also put something in it, yeah, it will change the meter, because right now it's an air core inductor. So when you put something in the inside inductor, right now the frequency is increasing. Right, which means I've lowered inductance by putting something in it. The value as it is right now, it's a particular inductance, but as I put this metal inside it, it changes the inductance, right? It makes the inductance to decrease and frequency to increase, right? Yeah. So the things around it affect the way it is stacked right over the battery also plays a role, because I think if I take it very so it took into consideration everything in this proximity to give me a particular value. As I change the conditions, that's why when you see those low quality wireless microphones used in functions or in churches or in programs, the very low quality ones, depending on where you're holding the microphone, the signal, there's one they call sound of heaven and stuff like that. They built around simplistic approach like this. When you hold the microphone at a certain point, the frequency changes just as good as your hand is coming over it. So the challenge here is that every single time my hand has to be on the same location. But when people talk, they don't really keep it. So if I try to move my hand, the frequency must go to another spot. Then I have to find where it is one more time. And it's so right now it's 82.4. Now when I change my hand, let's see where it goes. Right now it's 81.6. So one way to take care of this is to put a shield around it, an RF shield, so that the position of your hand will not affect it much. But this is a frequency. Right. If this transmitter was built around a crystal oscillator, you will not have this problem. One last thing I'll show you before we end today is, let's go back to the tutorial here. If you click, if you want to build a crystal controlled oscillator, just replace this capacitor with a crystal. A crystal also looks like a capacitor, the symbol, just a bigger blob in the middle. So do something like that, have this replaced by a crystal, and you don't need this frequency determining network anymore. You can have an inductor right there, and then have another capacitor to your antenna. The frequency will stable, and so the position of your hands will not affect it much, right? Inductance value might change, it will just be off a little bit, but the core frequency will remain the same, and then just take the feedback network as it is right now. So do this, let me know what you find out. Replace this one NF by a 27 megahertz crystal, and remove this circuit here. Just put any inductor here. You don't need this 30 picofarad or variable capacitor here. Just put any inductor here to complete the circuit. Replace this with the crystal oscillator 27 megahertz. And if you had purchased this SDR software defined radio, play around with it and see what you see on your spectrum. Alright, thank you, and I'll see you in the next one. Bye.